So what if the key to AI safety isn't about teaching an AI to be good? What if instead we could build a mathematical cage around it that makes it literally impossible for it to be bad? That's the really radical idea we're going to dig into today, a huge shift from trying to align AI minds to simply improvably aligning their behavior.
I mean, this is the nightmare scenario, right? The thing that keeps AI safety researchers up at night. It's called deceptive alignment, where an AI is all friendly and helpful on the outside, but its internal goals are dangerously misaligned. It's basically a ticking time bomb, and it's the central problem this whole framework is designed to diffuse.
Now, this is where things get really interesting. This is the paper's first and most radical principle. It says, stop trying to read the AI's mind. Seriously, forget about its internal thoughts, its motivations, none of that matters. The only thing that matters is what it actually does in the real world. This is a complete 180 on how a lot of people think about this problem.
Okay, so here's the game plan. First, we're going to wrap our heads around the core idea of aligning behavior instead of minds. Then, we'll peek under the hood a little and see the mathematical machinery that actually makes this work. And finally, we'll look at the incredible real-world promise this holds for things like governance and regulation.
All right, first up, let's really nail down why trying to trust an AI's internal reasoning is, well, a bit like trying to guess the combination to a vault that's designed to be unbreakable. It's just a fundamentally flawed approach from the get-go.
You know, the traditional methods we use, things like reinforcement learning from human feedback, which is basically giving an AI a treat for good behavior, they all try to shape an AI's internal values. The problem is, they're super vulnerable. We can't actually see inside the black box, right? So we have no way of knowing if the AI is genuinely on our side or if it's just a very, very convincing actor waiting for its moment to do something we don't want it to do.
So, let's pivot to the solution. Let's see how we can build a completely different approach to safety. The idea is, instead of trying to shape the AI itself, we're going to shape the environment it acts in.
The key here is a huge shift in what we're even measuring. We stop judging single, isolated actions. Instead, we analyze the AI's entire pattern of behavior over time as one single mathematical object. Think of it this way. You don't judge a movie by looking at one random frame, right? You watch the whole thing. We're going to do the exact same thing for AI behavior.
So if we have these movies of AI behavior, how do we know which ones are safe? Simple. We define it ahead of time. We create this universe of all acceptable behavior patterns, a mathematically defined safe zone called the aligned set. Any behavior, any movie that falls inside this zone is, by definition, safe. Period.
And this right here perfectly illustrates the core concept. The paper's second big idea is to completely decouple the AI's internal, raw plan, which we have to assume could be dangerous, from the safe plan that actually gets deployed. The AI can propose whatever crazy thing it wants. It doesn't matter. We make sure that what happens in the real world is always a safe, aligned action.
And this is how it works. It's a simple but really powerful three-step dance that acts like a mathematical guard. First, the AI proposes a plan. Second, an external monitor checks if that plan's movie is inside our predefined safe zone. Now, if it's not, the system doesn't just block it. This is the cool part. It projects it. It finds the closest possible safe action and executes that instead. So no matter what the AI wants, only a safe action ever makes it out.
Okay, this all sounds pretty great in theory, but how do we actually define this safe zone? How do we write the rules for our mathematical cage using concrete, computable language? The answer is with something called risk functionals. And don't worry, the name sounds more complicated than it is. They're basically just measurable rules that score an AI's behavior pattern. Think of them as the guard's rulebook, with really clear, simple instructions on what counts as a violation.
Now, for any of the practitioners watching, this is the really crucial bit. Safety stops being this vague, philosophical idea and becomes a set of explicit, measurable engineering constraints. For instance, we can write a rule to cap total energy use, which would stop an AI from secretly gobbling up massive resources. Or we can write another rule to limit how much sensitive data it keeps, baking user privacy right into the design.
So, we have the rules. But a rulebook is pretty useless without a guard to enforce it, right? How can we actually implement this monitoring system so it runs in milliseconds on a real live AI?
This is where the paper's third big idea comes into play. We stop the AI from hiding its intentions by forcing it to show its work as it goes. It's just like in math class. At every single step of its process, the AI has to spit out a structured partial output that our monitor can inspect. It can't cook up some complex, malicious plan in secret and only reveal it at the last second.
This operational loop is really the heartbeat of the whole system. It's running constantly. With every little piece of output from the AI, it checks for obvious problems, measures any drift from the baseline, and updates its safety certificate. And if any check fails, or if it just can't certify the action as safe, it immediately degrades to a safe response, like just refusing the request or even shutting down.
Okay, so what level of assurance does a system like this actually give us? What are its limitations? And, what does it mean for the people who actually have to manage AI risk in the real world?
This is not just some vague promise of safety. Because the whole framework is built on solid math, it allows for a mathematically sound certificate of safety. We can use well-established statistical methods to say, with a specific confidence level like 99.9%, that the AI's behavior will stay within our predefined safe zone. That's a huge deal.
But, and this is super important to understand, this is not a silver bullet. This framework doesn't solve what's called the specification problem. Think of it like this. It gives us a perfect, unbreakable safe, but it doesn't tell us what we should put inside it. It doesn't tell us what the right rules are. So it relocates the challenge from the fuzzy art of training AI values to the explicit, auditable engineering of defining and monitoring these behavioral rules. And for any decision makers or regulators watching, this is probably the most important takeaway for you. This framework provides a clear path to real, tangible governance. It imagines a standardized, machine-readable API that could be used to audit any AI system. It turns those vague safety promises from developers into hard, inspectable data that can actually be checked and enforced.
So we've connected our opening problem, that scary deceptive AI, to this powerful solution of a mathematical cage. So what can you do right now to start engaging with these ideas?
Well, depending on your background, there are some really clear small things you can do right away. If you're a learner, go look up Wasserstein distance. It's a way of measuring the distance between two distributions, which is how we can mathematically compare the AI's proposed movie to our library of safe ones. If you're a practitioner, try building a simple drift monitor. And if you're a decision maker, start thinking about how a concept like this certified check API could totally transform your approach to AI risk.
And this all brings us to our final thought. A framework like this doesn't ask us to trust the AI anymore. But that trust has to go somewhere, right? It asks us to trust the math. It asks us to trust the monitoring systems. And most importantly, it asks us to trust the people who write the rules for that safe zone. The alignment problem doesn't disappear. It just becomes a very human problem of governance, transparency, and oversight.